All right, so continuing in 7.1, we did the confidence interval by hand, and I want to show you that confidence interval on a graphing calculator. So let me do this. I'm going to specifically just share the graphing calculator with hopes that this doesn't freeze on me or mess up the video. So problem 18 on page 371 was the example that we looked at Monday. You saw how to use the table in your appendix section. If you're doing this on your graphing calculator, it's really nice. It's easy. I like this. I really like the ability to do pretty much the entire course on a graphing calculator. You would press stat. At the top, you'll arrow over to test. I'm just going to arrow to the left once. And what we want is option number 7, which is a Z interval. Okay, so I'm just going to press the number 7. All right, here's the data that I already entered ahead of time because I thought it might freeze up on me. You have an option of entering raw data, like whatever the sample size is. In this case, it was 40. You could enter all of those data items in list 1, and it'll calculate this based on the data. Or if you already have stats that you know, like sigma, x bar, and n, you would select stats, which is what we're going to do. For that problem we looked at, it was the watermelon price per 100 pounds, right? Sigma was 1.92, so you would enter sigma. X bar, the sample mean, $6.88, $6.88, right? And then we were looking at a sample size of 40, and we had a confidence level of 90%. So then you would enter 0.9, and then you would calculate. And just press enter. And you can see your confidence interval up here at the top. And remember, this is dollars and cents, right? So, and we calculated this by hand last class. $6.38 up to $7.38, round to the hundredths place if you're doing dollars and cents, right? So that's a nice, easy way to get your confidence interval. It's the Z interval. Any questions on that? All right, I'm going to clear that. Let's stop share and I'll go back to the notes. And it didn't freeze up on me. Nice. Okay. So now we're going to go down here and I'll give myself some space where I can show you some work for this. So we generally want to decide confidence levels in the error in advance in practical applications and research. And this means in real world practice, we want to determine a sample size n ahead of time for a particular confidence level. So how do we get that? Well, what we do is we use the fact that our error equals z sub c times sigma over the square root of n. And algebraically, if you solve that for n, you're going to get n equals z sub c times sigma, all of that divided by e in parentheses squared. So you guys have had algebra before, right? Up through college algebra at least. So all you're doing is solving this equation for the n, right? Tech notes on page 367 show you what I just showed you on how to calculate it on the graphing calculator. So what I want to do is we'll do the error, and I'm just going to write or do the sample size, and we'll do that for problem 18. So this is problem number 18 in this section. It's part B. And again, this is page 371. All right. So if you will remember, well, if not, I'm going to write it anyway. X bar was 6.88. Hold on. We don't need X bar for this. Hold on. Where's my information? Sigma for this problem was 1.92, $1.92. Sample size, we don't know. We're going to figure that out. The error this is part B. Find the sample size necessary for a 90% confidence level. With a maximum margin of error of 0.3. All right, so we have sigma. Now we need to find Z sub C. And I'm not going to pull up the table to do that, but we saw in the previous class how to do that using your standard table, table 4D, right? And for 90%, that was 1.645. So you have to get that off of the table, all right? So our sample size, we'll change colors here. Our sample size is going to be Z sub C times sigma in the numerator. Sigma times dot. There's sigma divided by the error that we want, okay? And we'll put that in parentheses and square it. And I'm just going to go by the answer that's in my book here. You round off to the nearest whole number, okay? So this turns out to be 111. And even on your graphing calculator or whatever calculator you're using, if that was 110.1, that 0.1 would make you have to round up to 111. If there's anything behind a decimal point like that, unless it's the exact value, you're going to want to round it up. Any questions on that? Okay. Which takes us to 7.2. I'm going to stop sharing and pause the recording here. Let's do it up here. No. All right, so here's the table in the back of your book, right? Hopefully that's what you guys are seeing. If not, let me know. So I'm going to go down and we're going to find, in this section, we're going to put something called a t-distribution. And it's bogging down over here. Of course, here's your Z distribution. Here's the second Z table where you have the confidence interval critical values that you need. And then we'll go to the next table. And we have what's called a student t-distribution. Let me go down just a little bit. So this is table 5 in your textbook. So what we're doing is confidence levels, right? And that's this first drawing right here shows you what you're doing when you're doing confidence levels. So what we'll need to do is, we're going to talk about this in the notes. This DF stands for degrees of freedom. And you can see it going down here. And let me just go down to the bottom of it. Notice once you get to 55, or excuse me, once you get to a certain point, 28, 29, 30, it starts going in like from 35 to 40, 45, and so on. 60 to 90 to 120, and so on, right? At the top, I'm going to write on this just a second. So you have your degrees of freedom going down this column, and then going across the very top where it's speed, that's what this represents. You're calculating a confidence interval, okay? So you would go down to the appropriate degrees of freedom, go across that top row, and then wherever they meet, you would find inside the table the corresponding value. That's the area under the curve, okay? Any questions on that? All right. So let me, let's go back to right? No, that's not right. There we go. All right, sorry about that. All right, so back to 7.2. So in 7.1, we estimated mu when sigma was known. Most of the time, sigma is not known. I talked about that during class last time, and we talked about that in the video as well. So then how do we develop a confidence interval for mu? Well, what we do is we use the sample standard deviation S to approximate sigma. And when we do that, we're no longer in a normal distribution. We're going to be using what's called a student's t-distribution, and that's that chart that I just showed you. So if X is normally distributed with sample size n, you can change X bar to a t value instead of a z value. And it's the same process. If you take a look at this formula right here, to change X bar to z, it's very similar, or to t, it's very similar to z. You do X bar minus the mean, but instead of dividing by sigma over the square root of n, you're dividing by S over the square root of n. And the degrees of freedom, that first column that we looked at on that table, that's n minus 1, sample size minus 1. There's a lengthy proof that goes into showing that. We're not going to cover it this course. Take a look at page 375 for properties of the t-distribution. What I want to tell you, I'm going to do this really simple here. I'm going to draw a real quick drawing of a t-distribution. A t-distribution looks very similar to a standard normal distribution. And the high point is at the mean, except the tails of the t-distribution are, for lack of a better term, fatter than for a z-distribution. It slopes down slower towards that horizontal asymptote, if you will. Okay, so I'll mention those properties, and then you can take a look in your book at page 375 for other properties of it. So the idea here is to construct a confidence interval similar to what we did in 7.1, but instead of our error being z sub c times sigma over the square root of n, our amount of error is t sub c times s over the square root of n. All right, any questions on that? Because I'm getting ready to show you an example. And again, check it out. You know, once you find the error, you're just doing X bar plus and minus whatever that error is. Right? So I have a bunch of space here using the t-table. Well, now you'll get to see it. And then we'll go over how to do it on a graphing calculator. Let me do this. I'm going to pause the recording. All right. So we're on page, for this problem, we're on page 383. Problem number 14. Okay. Now, check this out. For problems that I've assigned in this section, they actually give you the data. So for problem 14, they have 25, well, let me just read it. It concerns the cost of a sleeping bag. How much does a sleeping bag cost? Let's say you want a sleeping bag that should keep you warm in temperatures from 20 degrees to 45 degrees Fahrenheit. A random sample of prices for sleeping bags was taken, and this is that, and then they give you the book that this was in, Backpacker Magazine, rather. And different brand names of sleeping bags were tested. And so they actually give you 20 pieces of data. And then they want you to plug it in a calculator just to confirm what part A tells us. And I can tell you right now, when they say use a calculator to verify this stuff, it is true. So you could skip part A for something like that, all right? Part B is what we're interested in. Using the given data as representative of the population of prices, find a 90% confidence interval, all right? So we're given in part A, we're given that X bar is $83.75. And we're given that the sample standard deviation is $28.97. Ooh, that's fine. Try that again. $28.97. Our level of confidence is 90%. I'll just say 0.90, okay? Any questions on that? So that's my given information. So now what I need to do is find the t-value corresponding to this, all right? So before I pop the t-table up, we know that n is 20. So I know my degrees of freedom, n minus 1, that's going to be 20 minus 1, and that's going to be 19. Any questions on that? All right. Bear with me. I'm sorry. Give me just a sec. I don't think I recorded any of that. All right, so we found our n is 20, X bar is 83.75, S is 28.97. We want a confidence level of 0.90, 90%. Our degrees of freedom, sample size minus 1 is 19. We need to find the t-value for that 90% interval. So if you look at this t-table, you go down on degrees of freedom to 19, go across to 0.90, go down, it's 1.729. That's my t-value for 90% confident. My error is the t sub c s over the square root of n. 1.729 times 28.97 over the square root of 20, that's approximately 11.2. So X bar plus and minus the amount of error, 83.75 plus and minus 11.2 is 72.55 as a lower bound, 94.95 for the upper bound. So we can be 90% confident based on this sample that the population mean price is is between $72.55, $94.95. Thank you for your patience. All right, you should see the graphing calculator up here now. If not, let me know. All right, so how do you do this on a graphing calculator? Well, we go into stat and we go over to test again. I'm going to arrow over this way. Now, 7 is a z interval, right? We are now doing a t interval. And it should be 8. Yeah, so it's option number 8 is a t interval. We're going to enter. And again, we're entering stats. You could enter the data on your calculator and do that, but they already give us the information we need. X bar is 83.75. Our sample standard deviation on your calculator, it calls it SX, and then 28.97. Now check this out. You don't need you guys with your calculator, you don't need to look at the table for this. You don't need to calculate the error, right? Sample size here was 20. And we want a confidence level of 0.9, which was already in here from a previous problem. So it's 0.9, we'll calculate. And there's our interval. Rounded, you'd have to round it to the hundredths place for dollars and cents, right? Any questions on that? Okay. And what I just showed you with this graphing calculator is the tech notes, essentially. Referred to here on page 377. So let me, again, bear with me. I'm going to pause this. Zoom recording. All right, so now we're taking a look at 7.3, section 7.3. You can also use these methods of estimation to estimate P. That's a population proportion of successes in a binomial distribution. P, remember, is the number of successes. Q is the number of failures, and Q equals 1 minus P, right? The sample statistic that we're going to use, P hat, that's our sample point or our point estimate sample statistic we're going to use to estimate P. Q hat, 1 minus P, we're going to use to estimate Q, or I should say 1 minus P hat. Let me correct that. Another typo. And so the error for this, and notice this is a Z distribution. If NP and NQ are both greater than 5, which in the problems you have assigned they are, NP and NQ are both greater than 5, then it is a normal distribution. So you can use a Z distribution instead of having to use a T distribution, all right? The error is approximately Z sub C times the square root of P hat times Q hat divided by N. And so then we just do P hat plus and minus the error, and that's our confidence interval. And example 6 on pages 390 and 391, I think I'm just going to go in and do example 6 on here for you, okay? And actually it starts on pages 390 and 391. So this is a flu shot related to flu shots. So we have, let's do this over here. So we have a student body of 20,000 students, and out of those 20,000, they were given 800 were selected and given shots to prevent a certain type of flu. So we have 18 students were given shots. All of the 800 students were exposed to the flu. 600 of them did not get the flu. Let P represent the probability that the shot will be successful. So it's successful if they don't get the flu, right? Be successful for any single student selected at random from the entire population of 20,000. And Q is the probability the shot was not successful, the probability of a failure, right? So the N is 800. The number of successful trials is referred to as R. That's what you see up here. 600 did not get the flu. So we need to know P hat. Which is R over N, right? And you pop that in on your calculator, and you get approximately 0.35. When you calculate Q hat, that's 1 minus P hat. So 1 minus the 0.35, and you get, what do you get? .65, yeah. All right. Then technically you would check to make sure that that the R, actually the N times P. No, hold on a second. I'm looking at the wrong thing here. Yeah, forget that. I'm just telling you incorrectly there. So never mind. Right. So now we need to find the 90% interval. So we need to find Z for 0.95. not, I'm sorry, 90%, 90%. And that was the 1.645. All right. They want a 90% interval. And so then we calculate the error. Calculate the error, which is the 1.645 times the square root of p hat, which is 0.35 times q hat, which was 0.65. And then we would divide that by the sample size, which was what, 800. And we plug that in on our calculator. I'm doing something not right. Crap, I just mixed problems up. I hate it when this happens. Give me just a sec. I'll have to edit this part out. For this example, I mixed up examples. They want a 99% confidence interval. So our Z value for 99% is 2.58. All right, sorry about that. So our error is going to be approximately the 2.58 times the square root of p hat times q hat divided by sample size, which is 800. And that is approximately 0.0395. All right. And then we do the 0.35 is my p hat. Plus point p hat. You know what? Give me just a second. I gotta go back and change this. I'm sorry. I gotta change this too. Again, because I mixed up examples. That p hat 600 over 800 is actually 0.75. And this is actually 0.25. I apologize profusely for that. Try this again. .0395. That's what I get for mixing problems. So then we want p hat plus and minus the amount of error. And that's going to give us a confidence interval rounded to the hundredths place. 0.71 is somewhere in here. 0.71. Let me do this. Previously, I did it just with separated by comma and parentheses, which is correct notation, but I'm going to write it like this. So based on this particular sample, we can be 99% confident that P is somewhere between 0.71 and 0.79. Any questions on that? And again, I apologize for the mistakes on that, which I'm going to edit out. Now let me show you how to do this on a graphing calculator, and then we're done. And I won't see you again till Monday. So what you should be seeing right now is my graphing calculator. We'll go to stat, we'll go to tests, and this one, I gotta go down because I don't remember the number or letter. Here's what we want. That looks like A as far as I can tell after the 0. We want the 1 proportion Z interval. So I'm just going to press enter. What we call R in our textbook, your calculator calls X. So that's 600. Sample size is, or excuse me, yeah, N was 800. And we want our confidence level to be 0.99. And then we'll go down and calculate. Oops, don't do that. So yeah, we get to the hundredths place 71, and for the upper bound, it would be 79. Any questions on that? All right, now I will stop recording.